This video is a makeup presentation for a lost day of class due to snow for our Math 232 course. To start, I want to remind you that in introductory calculus we learned that we could graph the function f if only I knew things about the sign of f prime and f double prime on certain intervals. The problem with that is that knowing things about the derivatives don't actually tell me about the height or position, or at least they didn't until we learned about definite integrals. So I want to start by reminding you of what we already know. In this example, I have a function. I don't know the function, but I have sign analysis for both the first and the second derivative. The sign analysis tells me that the first derivative is positive for x less than 0, and so my unknown function is increasing for x less than 0. I'm decreasing from 0 to 3, and I'm increasing from 3 to infinity. The second derivative gives me information about concavity. So for example, the second derivative is negative for x less than 2. This tells me that my function will be concave down for x less than 2. Similarly, my function will be concave up between 2 and 4, and concave down for x greater than 4. In order to understand what the graph would look like, I create a curve number line. And every mark on the first or second derivative, I'm going to mark down. And for simplicity, I'm going to mark all the first derivatives in red, and all the second derivative marks in blue. Now, based on the sign analysis, between 0 or less than 0, my function needs to be increasing. So if I imagine a positive slope, I get a curve like that. But I also know that I'm concave down. And so my curve is going to be a increasing concave down shape. Once I pass 0, my slope becomes negative. So now I'm a decreasing function. I'm still concave down, so my curve will bend down still. Once I pass 2, my concavity switches. So my slope is still negative, but now my curve is concave up. At x equals 3, I switch to increasing. Still concave up. And after 4, I'm still increasing, but I'm concave down. In order to graph my overall function, what I'm going to do is I'm going to have to attach these different shapes in different regions. What are some of the basic features that we need to capture? Well, I have a maximum at x equals 0. I have an inflection point at x equals 2. I have a minimum at x equals 3, and I have another inflection point at x equals 4. The first derivative test is what told me that if I go from increasing to decreasing, I should have a maximum, and if I go from decreasing to increasing, I should have a minimum. So if I were to try to graph my original function, we're now stuck with the fact that we don't know enough information about our curve. We don't know what the height is. So for example, I could pick my maximum at x equals 0 to be right at the origin at height 0. And then I've got a curve that's increasing and then decreasing until x equals 2, where I have my inflection point. Let's mark some other x values here, 3 and 4. Again, I don't know where the minimum is, so, well, I know it has to be below the inflection point, but I don't know how far. And then 4 is some other inflection point. I really don't know where it is. So I'm going to be concave up between those points. Let's try that again. Concave up. And then after 4, I'm concave down. My graph is compatible with another curve that has a inflection point and a maximum. So let's draw our curve, followed by a minimum and our inflection point. That has a different relationship between my points. So for example, notice that my orange curve has its asymptotic behavior below the maximum, while my purple curve has its asymptotic behavior above that maximum point. And based only on the sign analysis, I have no idea which curve it is. Well, this is the information that a definite integral provides. Since the function we're looking for is actually an antiderivative of the graph we see, f prime, the fundamental theorem of calculus tells us that the change in our antiderivative f of x between any points a and b must equal the definite integral of f prime. And so if I can calculate the definite integral, f of b will equal f of a plus that definite integral. And this will allow us to calculate actual heights, as long as I can do the definite integrals. So let's consider this example. The graph of f prime is shown. Here's x, y equals f prime of x. We know that f of 1 equals -2. We want to find f of 6, and the fundamental theorem of calculus tells us f of 6 equals f of 1 plus the integral between 1 and 6 of its rate of change. Now, if I think about the graph, the integral from 1 to 6 is simply calculating the signed area of this region. Now, the way that my function f prime is illustrated, I can see that there are basic geometric shapes. So for example, in this first region between 1 and 2, I have a single square. The width is 1, and looking at the height, it's also 1. So this area is 1. If I think about what's next to it, I have a triangle, which is exactly a half of a unit. It's half of a square. I then have another region. It's a triangle. Its width is 2, its height is 2, and so its area is 1/2 of 4, or 2 square units. Finally, this last region has an area given by a width of 1 and a height of 2. The area is 2. So my height at 6, f of 6, of the function that I don't see, is f of 1, negative 2, plus, if I were to think through all the steps, it'd be the integral from 1 to 2 of the function. That's the square. Plus the integral from 2 to 3 of my function. That's the small triangle. Plus the integral from 3 to 5 of my function. That's the big triangle. And the integral from 5 to 6 of my function. And that's the narrow rectangle. The first two integrals correspond to negative areas. And so my area 1 gives a contribution of negative 1. The second integral, which was my orange triangle, gives a contribution of negative 1/2. At this point, my last two regions are above the axis, and so the integral from 3 to 5 gives a value 2, and the integral from 5 to 6 gives another value of 2. Consequently, the net change of the integral is 5/2. 5/2 is the integral from 1 to 6, and that's how much my graph changes. When I add negative 2, I get a total height of 1/2. So the definite integral, here calculated geometrically, allows me to know what the height of my function will be. Well, if I extend that idea and think about not just the one point that we just calculated, but think about every step along the way, I can actually get a sense of what the entire function f looks like. So we know f of 1 equals negative 2. This tells me that I can now calculate f of 2. This will be f of 1 plus the integral from 1 to 2 of my derivative. That reminds me, I might have actually said the wrong function on the previous slide. Let's take a quick look. Yep, each of those functions in those formulas, my 4 integrands should have been integrating the derivative function, because that's the function we actually were looking at. That was sloppy on my part. Well, let's go back. F of 1 we knew was negative 2. The integral from 1 to 2 is a signed area of negative 1, giving me a net value of negative 3. To calculate my function at 3, I could either start at 1 and do the integral from 1 all the way to 3 of the illustrated rate, or I could have done f of 2 plus just integrate from 2 to 3. The new area that I'm adding is the area of the little triangle, which has area at 1/2. So I'll get negative 3 plus another negative 1/2 for a total of negative 7/2. F of 4, I could start from any point now, but it's easiest to think, okay, we've already made it to 3. Let's now go from 3 to 4 of our rate. So I get negative 7 halves. And the integral from 3 to 4 is a triangle with area 1/2. This time it's above the axis. And I'm back at negative 3. Interesting to point out that we are back at the same height as we were at 2, and that corresponds to the fact that the area that we've seen above and then below exactly cancels. So every time we have these balancing areas, we should see that we're at the same heights. Okay, if I keep going and go to 5, f of 4 plus the integral from 4 to 5 of my rate. So we are at negative 3, and that area corresponds to a rectangle and a half triangle, or a half. So it's plus 1.5. F of 6 is f of 5 plus the integral from 5 to 6, which is a rectangle, so we get negative 3 halves. That rectangle has height 2, width 1, giving me a value of a half. Which agrees with what we had calculated earlier. That's always good to check. And as I keep going, I'm not going to write the integral again. F of 7 will be a half plus another 2, so that's 5 halves. This came by adding yet another rectangle. And if I imagined 8, which is not on my picture, I would need to calculate what this area is, and it appears to be another 1.5. So f of 8 would be 5 halves plus 3 halves for a total of 4. Well, we've worked to the right. We need to also think about working to the left. So we've done f of 1, let's do f of 0. The formula actually says we can still do the same thing. It's f of 1 plus the integral from 1 to 0 of f prime. The thing is, this integral is a reverse integral. I'm going backwards. So I really need to interpret this as the value of at 1, that's negative 2, and then I'm going to subtract the integral from 0 to 1 of f prime of x. The area in the square was an area of 1. The area was 1. So the integral from 0 to 1 of f prime, signed area, is negative 1. And so if I integrate from 1 to 0, I subtract negative 1, giving me a value of negative 1. If I were to go back one more unit, f of negative 1, I would get negative 1, and then I would subtract yet another negative 1, to give me a value of 0. And that's because the integral from negative 1 to 0 of f prime of x dx is actual signed area of negative 1, corresponding to being this square under the axis. And when I go backwards, the integral from 0 to negative 1 of my derivative would be positive 1. Which is why I add negative 1 plus 1 to give me 0. So as I prepare to graph my function, I've added some axes, and I can now plot my points, and we can now sketch our graph. Notice that between, well, up until x equals 2, my graph has a constant slope. The derivative was constant. So my antiderivative is going to be a straight line. Also, from 5 to 7, let's see, where's 5? 1, 2, 3, 4, 5. I also have a straight line. But between 2 and 5, I have my slope is increasing, which means I'm a concave up shape. So my curve is concave up from 2 until 5. Similarly, between 7 and 8, my graph is concave down, although it's hard to see with just a single point. And so the antiderivative is what's giving me the power to be able to understand what the shape of this graph looks like. On Blackboard, there's a file, a PDF file that I want you to download, and it gives you a graph of a derivative function. And I want you now to go through the process of finding the value of the points of the function f based on the graph of the derivative. And I'll see you on Monday. Have a great weekend.